On limits of function, we are going to explain what limit of function is and give examples. Click like, subscribe, and press the notification button for you to be notified whenever we drop a new content. You can also share for others to see. Consider this function. Let us look at this graph of this function. Okay, this is our normal x-axis and this is our y-axis or f of x. So this is the function f of x being plotted. Now if on this x-axis we can pick a point, let's say we pick a point A, okay, then the corresponding value of the function is when we trace A to this graph, and then we find the value on the y-axis. So here, if for the point of A, then the value of this function, let's call it L. Okay, now we can remove some small number from A, then we call this point, let's say A minus small number delta. Then on the right, we can also add that same delta, A plus delta, such that we have this interval. Okay, so for this interval, we can also obtain the values of the function. So here we are going to have this point. You see that the value of L has been shifted from L to some, let's say L minus epsilon, and then let's say the value for here too has been shifted as well to some L plus epsilon. Okay, now for any point x that you pick on the x-axis within this interval, as the number approaches A from the left or from the right, so you also have corresponding shift in the value of the function on the y-axis. Okay, so we can write that the limit as x tends to A from the left of the function of x gives us a particular value, let's say L, and then the limit as x tends to A from the right, we say A positive of the function of x gives us some number m. Okay, the values may be different and may be the same. When the values are the same, we simply say that the function is a continuous function. But when the numbers are not the same, then it's going to be a discontinuous function. Okay, now if L is equal to m, if it's the same thing, then we simply write that the limit as x tends to say A of the function of x then is equal to L. That is, if m and L are the same thing, then we simply write limit as x tends to A of f of x is equal to L. Okay, so this is one way of defining the limit of a function. We can also define the limit of a function as if, that is, if we are given any epsilon greater than 0, then there must exist a delta that is also positive, such that the distance between x A, if less than delta, this will mean that the distance between the function and the limit, okay, the function and the limit must also be less than epsilon. Okay, so these are the two equivalent ways of defining the limit of a function. Let me give you an example. Let us find the limit as x tends to 2 of minus 3x plus 3. Okay, so what we do here is you just simply assume that x has approached 2. Okay, so this is just done by direct substitution. You just put minus 3 times 2. Okay, you substitute 2 for x plus 3, and then you obtain minus 6 plus 3, and then this limit is going to be, that is first definition. So you can also write this same thing in regard of the second definition. Okay, so it means that we have 0 less or x minus A is 2. Our A is 2, x minus 2 is less than delta. It will imply that f of x, which is our minus 3 plus 3, okay, then minus the limit that we got is this minus 3 here. So that is minus 3, and that must be less than epsilon if evaluated. And to see that, you notice that we can actually write this as minus 3x plus 3 and then plus 3. Okay, that will give us absolute value of minus 3x plus 6, which is, or can be written as, we can factorize 3, that's x minus 2. All right, so but here we have said that we can take this absolute value of x minus x2 is less than delta. You can take it as delta. So this means that we can separate the absolute value of minus 3 and absolute value of x minus 2. Okay, and that will give us absolute value of minus 3 is 3. So that's 3, and x minus 2 will take it as delta. Okay, so to achieve this epsilon here, we can take this delta, you can take delta to be epsilon over 3. So obviously we are going to obtain that absolute value of minus 3x plus 3 minus 3 is actually less than epsilon, which shows that the limit of this function as x tends to 2 is actually minus 3. Okay, now let me give you an example. Some example may not require direct substitution. Evaluate limit as x tends to minus 2 of x raised to power 3 minus 4 over x squared plus 1. Okay, so these two can be done by substitution. You should always check for direct substitution first if it works. If it does not, make the function to be undefined. So in this case now, direct substitution will give us minus 2 raised to power 3 minus 4 over minus 2 raised to power 2 plus 1, and then we get, that is a minus 8 minus 4 over 4 plus 1, and that gives us minus 12 over 5. This will be the limit of this function as x tends to minus 2. But some problems may seem to be different. Look at this. If we are to evaluate, say, limit as x tends to say 1, x squared minus 1, let me use minus 1 over x minus 1. If you try direct substitution here, that will be a problem, because we're going to have 1 squared minus 1 over 1 minus 1. So you get 1 squared is 1 minus 1 over 1 minus 1. So you get 0 over 0. This is what we call an indeterminate in mathematics. When you encounter something like this, you must look for alternative way of doing this problem. So this will be very wrong. What you can do, this difference of two squares, because we can write this as limit as x tends to 1 of x plus 1 and x minus 1 over x minus 1. Okay, remember difference of two squared, because this is x squared minus 1 squared, the same thing. So, and this implies that x minus 1 takes care of x minus 1. So our problem has reduced to limit as x tends to 1 of x plus 1. So we now try our direct substitution now. Then we have x plus 1, that is 1 plus 1. So the limit is 2. So instead of having 0 over 0, the limit is actually 2. Let us evaluate x raised to power 2 minus 9 divided by x minus 3. Direct substitution will also give us problem, because if you put 3 at the denominator, this function becomes undefined as well. We're going to have the 0, and you must always avoid that in mathematics. So what you should do is you can as well expound the numerator because that's difference of 2 squared, as x squared minus 3 squared over x minus 3, and that is limit as x tends to 3, okay, of x minus 3 times x plus 3, same thing that we have just done in the last example, x minus 3, okay, and this takes care of this. So we are left with a limit as x goes to 3 of x plus 3. Then the direct substitution will now give us 3 plus 3, and the limit of this function as x tends to 3 is now 6. Okay, some limits of other function may require more technicalities, okay, and I'll give such examples in the next video. But note that the limit of sum of functions, it is the same thing as limit of f plus limit of g. Okay, then limit of the product of f and g is same as the product of their limits. Okay, limit of f times limit of g. Limit of quotient, that is f over g, is the same as the quotient of their limits, limit of f divided by limit of g. Okay, but this provided that g is not equal to 0. Okay, you must always avoid that at the denominator. So see you in the next video when I will give you more examples on functions whose limit requires more technicality. Kindly share and subscribe and press the notification button for you to be aware when I post another video. Thank you.